Welcome to Penrose Learning, where we make understanding easy.
You begin by confirming where the original function exists and is smooth, because the derivative only lives where differentiability holds. Once done, compute the derivative expression algebraically when possible. When not, use the limit definition at targeted x values to get precise slopes. Make sure to mark points where the function is continuous but not differentiable, and list critical x where derivative equals 0, becomes infinite, or fails to exist. These initial values are the anchors for the entire derivative graph. Now sample the derivative across the domain. Plug into your derivative formula to compute exact slopes at roots, endpoints, and a dense grid of x, so you capture behavior between special points. Once done, analyze sign on each interval to know where the original increases or decreases, and observe slope magnitude to infer steepness. Make sure to locate zeros of the derivative for local extrema and sign changes for inflection. This collection of points and signs dictates the derivative curve's overall shape. Finally, plot the derivative points you computed and connect them with smooth arcs wherever differentiability holds, leaving gaps or jumps at non-differentiable x. As you draw, enforce asymptotic behavior and vertical blow-ups seen from the derivative formula. Align increases and decreases with the sign analysis. Make sure to verify by picking a few x and comparing your sketched derivative value to the slope of a tangent on the original function. Troubleshooting tip: if mismatch appears, recompute slopes at nearby x and refine your sampling density.
Thanks for watching. If this was helpful, leave a like and consider subscribing. See you next time.